Okay, I start with thanking the organizer for giving me the opportunity to present this work. So this work has been with the collaboration with few people. This is actually that we are doing some sort of a model independent study to study this the Hubble tension with the low redshift and high redshift observations. And as an end result, we got a surprising result that there's maybe some sort of a new energy density component that you have to include, and if you include that, that may give some nice results. So I'll be talking about that. Okay, we all know that there is a huge dark energy component, and after the Planck 2018, the Lambda CDM, the concordance Lambda CDM model with these 6 parameters is an excellent fit, not only with the Planck, but also the other observations like supernova, baryon acoustic oscillation, and other things. And from that, there are other parameters also you can constant very well, and in particular the H0, which is the expansion rate at present, and these are the very nice constraint. And the problem is actually with this. So, but one can go beyond the cosmological constant and try to fit with the evolving dark energy, mostly with this CPL parametrization. And then also obviously the cosmological constant is quite consistent, as you can see. Just to tell that even if the cosmological constant is very much consistent, but if you want to go beyond cosmological constant, you can see there is this region actually. This region is where the dark energy is non-phantom, and there's a very small region of space where actually you can have any model which is non-phantom. Most of the other models that you can get from CMB is actually phantom region. So this is an interesting observation. But okay, so here also if you go beyond Lambda CDM, the cosmological constant is quite consistent. Okay, so where is the problem? So the problem is in this picture. So as I said, that this H0 that measured by Planck, which is around the value of 67, but the low redshift observations like from Rishi, from supernova, with the supernova or the strong lensing and everything, mostly the Rishi, they have a huge around more than 3.5 sigma tension with this Planck result. There is a little tension with the Bose-Lyman alpha observations about this H value from the Lambda CDM, but the more important is this tension. Okay, so the fact is that we try to see that how one can actually resolve this thing. Okay, just looking at this plot, if you think that the Lambda CDM is more or less consistent in most of the time of the evolution, but at the present time we need some model or something that we can take this value to here. It seems that as because matter, you cannot do with anything, so only thing that you can change is the dark energy. So maybe the dark energy density has to increase around the present time, and increasing dark energy intensity is nothing but that it has to be a phantom, fine. So that may be one possible resolution. Okay, so this is the tensions in more quantitative way. So this is the thing that the Planck measured, and these are the results from the low redshift by Rishi, and yesterday also the strong lensing measurement, that is also this. Probably the error bar is a little high, but still this value is more consistent with this low redshift measurement than the Planck measurement. Okay. Okay. So the point is that once this tension is there, what is the implication in the possible dark energy behavior? So once you have this Einstein's equation, for the timing for the low redshift case, I just ignored the radiation. So you mostly have matter and some effective dark energy. I call it effective because even if you have some interacting dark energy or what sort of modified gravity and model everything, I just take out the matter behavior from it, and rest of the things, whatever is there, I call it as an effective dark energy. Okay. So how one can constant this? One way is that mostly people do is that you assume this energy density to be a positive thing, and then assume a equation of state for this dark energy, and then you try to constant this equation of state because the rho dark energy is now proportional, means depends upon this equation of state, and try to constant this behavior of the equation of state. The other is that you don't assume anything about this part. Okay, it can be positive, it can be negative, and you directly, if you have some quantitative knowledge about this H square from the observations, then you know the matter. Okay, and then you try to reconstruct this effective dark energy density. Okay. So for the first approach, there is a nice paper in 2017, the Nature paper by these people, and they reconstructed this W of this dark energy density with all these results from Rishi or Planck. That time the Planck 2015 results were there, and they get this equation of state behavior. Okay, which is pretty weird because it has all this oscillation in the equation of state. This is the lambda CDM, and then means the cosmological constant, and it got oscillate around cosmological constant. It has phantom, non-phantom, and all these oscillations are there. Okay, so which is very, very weird. You can also do the other one, which is this one, that you don't assume anything about this or equation of state. Just from here, you try to reconstruct this, okay, giving the knowledge of h square from different observations. So they did it, okay, and this xj is actually this energy density of the dark energy as a function of redshift, and this is their reconstructed behavior, okay. As you can see, this reconstructed behavior, it has this oscillation kind of thing around this one, which is for the cosmological constant, this is just 1. Not only that, it actually goes to negative at pretty high redshift, means as you go with the redshift, it actually goes to the negative values, okay. This is the pressure of this dark energy that you can reconstruct. This also has this oscillation. And the H that you have, and if you divide it by the H as measured for lambda CDM model by Planck, this H also has this oscillation, fine. So it goes like the value of H actually goes over the Planck value or less than the Planck value, and it oscillates around it. So this paper came very recently. Same result has been also obtained by these people, Kaminkowski and their other collaborators. And they also reconstructed in a different way this H, okay, taking account that there is no equation of state, just try to reconstruct this H. And they also got this value. So see, this is assuming a positive prior, and this is without any positive prior. And they also get this result. The energy density of the dark energy, there goes to the negative value at some high redshift, okay. And the fact that if you take all these results, especially the Lyman alpha, the H naught and everything, the energy density at some high redshift go to negative values. This also has been confirmed by these people, Bounshani, Arman, and Starobinsky. And also in the Boss collaboration, the Delubach paper, Ittal paper in 2015, they also confirmed this, and they said that they actually got a constraint on this raw dark energy at redshift 2.34, modulo at redshift 0, which is around minus 1.2 plus minus 0.8, okay. But this energy density, effective dark energy density going negative is not a problem, because if you have a kind of a scalar tensor theory kind of model, if your effective energy density looks like this, so even if this part is not negative, but you can have some sort of a F which can make you the effective dark energy density to be negative, okay. It's not the actual energy density in this phi field is negative, but in an effective way it can go to negative value. But there is a problem, okay, because when you have a specially flat universe, this thing is 1, and if this part goes to negative and it's unbounded from below, if it is just going negative and going negative, then at some point omega m will be greater than 1 and it will increase without any bound over 1, fine. And that can spoil your large scale structure observations. So that is the thing that we need to solve, that okay, it's going to negative, but whether we can stop it and it has some minimum and then again rising, and how one can solve it, okay. So the way that we approach this problem is that we only take the background cosmology results from the low redshift. We go with a cosmographic thing where you can write H in terms of its defined derivative, but the problem is that as you go to higher redshift, that all these things can blow up, fine, because at higher redshift it doesn't work. So to make this convergence at high redshift, we use this Paddy approximation, which is the ratio of the two rational function. And we use this Ez, which is the normalized Hubble function, as an order 2 Paddy approximation. And we use all those data, okay, the low redshift data. For that, I mean, we're not using any CMB. So this is our H, which also shows the same behavior as I showed that the other people showed, that the H modulo H Planck lambda CDM has an oscillation. The dark energy density also has this behavior that it has this oscillation around the lambda CDM value, or the W equal to -1 value. But interestingly, this is our H by 1 plus Z. Okay, so as you can see that this has now consistent with this. It is also consistent with Lyman alpha thing. So this is the comparable result. But it's also going, so this is going this direction, fine. And these are the 3 points that I put just to show that if you just take this Planck result, go to some high redshift, we just generate some points over here. So this is obviously not consistent with the Planck HZ behavior, okay. And this is the FZ, which is nothing but this raw dark energy, is also going to negative. And these have this oscillation around the very present time. So all these results are confirmed with previous people that has obtained, fine. So what we now did is that we just put a sort of constraint that this behavior has to match with the matter-dominated universe as given by Planck. Okay? And where this matching can happen, so we take just two redshift. One is redshift 4 or beyond, or redshift 6 and beyond. And then we say that, okay, whatever you are getting, it has to match with the matter domination with the Planck lambda CDM, okay? And then see how it happens. So now this is my HZ behavior, okay? So these are these Planck points. So this is the two cases where it is matched at 4 or matched at 6. These are the Planck points, and these are the other thing, okay? So this is now quite consistent with all these results. What is the repercussion in the energy density of the dark energy? So this Fz, which is the energy density of the dark energy, which is going negative, but now as it has to match with the matter domination, it now attains the minimum over here, and then again goes back, and it matches to this constant 1 value at the lambda CDM at the high redshift. So what we get is that just matching this with this lambda CDM behavior or matter domination at high redshift, as given by Planck, it get a minimum. Now what is the okay, so these are the omega m, omega dark energy, and other the pressure behavior. So this is the omega dark matter behavior, this is the omega dark energy behavior, and this is the pressure. As you can see that it has some small negative value, which gives you this omega m a little bit higher than 1 at some redshift. Otherwise it is fine. And we also just check with this H behavior, we calculated the CLTT, okay, and we compare with the CLTT with the Planck result, and it seems that it is quite fine. Means we have not done the full cosmology, but as just a check, this is not very sort of different from what the Planck points are. Okay. So what is the repercussion of this negative? Fine. So at the negative, your rho dark energy density, the derivative is 0. That means this is 0. So that means the obviously is a cosmological constant. But as because this rho dark energy density is itself a negative, so this cosmological constant is a negative cosmological constant. Okay. So what we have that this at the negative, you have a presence of a negative cosmological constant. So what you can have now, so whatever you have this H square, that gives you a rho total. You take out the matter part from there, that we have reconstructed. So this has this nice oscillatory behavior and with a minimum, negative minimum. And then you just take this negative minimum that you have, take out. Then there is a dark energy behavior which has a phantom to non-phantom crossing, plus a small negative cosmological constant. If you assume this, as I showed, that H by 1 plus Z, that graph and everything is quite fine, and that behavior is quite consistent with the Planck CLTT. But as I said that at some point omega m going a little bit 1 greater than 1 because the omega dark energy is little less than 1. And if you have that thing, then obviously at the large scale structure there you have some repercussion on the large scale structure behavior. That the nonlinear regime may start little earlier, there can be some more massive galaxy at the high redshift, and these are the definite prediction that you have for this model which is falsifiable. So you can definitely check it with the upcoming surveys. So here is my conclusion, that this lambda CDM is the simplest model, but there is all these tensions are there. And we try to solve this tension in a model independent way. Our results is quite consistent with the other results that people have obtained. But then people have not put that matter bound, that it has to be matter dominated at the high redshift. We just put the bound, assuming that this matter domination is as given by Planck for a lambda CDM model. And so once you assume that, it seems that the total dark energy density that you have, you can take out a small but negative cosmological constant, and the rest of the part is a dark energy which has some phantom, non-phantom crossing. Okay. It has some definite signature on the large scale structure, giving the fact that there's some effect on there'll be more massive galaxy, your nonlinear scale or regime can start early and all those things, and this can be tested. This can be tested quite clearly. So it seems that, okay, so I mean, forget about this pad or all those things. So if you have a model of dark energy which has a phantom crossing, but a small negative cosmological constant, that behavior, now you take that dark energy behavior, a phantom crossing coming from any field that your favorite, put a small negative cosmological constant. The H behavior, at least for the time being, is quite consistent with the defined observations. And the CLTT or this thing that it produces is also, it seems, apparently not very much different from what the Planck predicts for lambda CDM. Okay, so that's the thing that I need to say. Thank you very much for your attention.
Thank you.